Okay, so we start with magnetism, and before I start the chapter, let us do some little bit of zero level talk that we do before starting any chapter. Okay, let's do some zero level talk to develop initial idea about this chapter. Magnetism. Now, one of the effect of electric current is magnetic effect of current, which means with electricity, you should be able to create a magnetic field. So, the process of irreversibility is something that scientists always think about. If I can make ice out of water, I should be able to make water out of ice also. So if you can generate magnetism from electricity, then there should be some way in which electricity can also be generated from magnetism. That is the part which we study in electromagnetism. Unfortunately, in your syllabus earlier, electromagnetism portion was there, like studying about generators, motors. Now, if you see the new syllabus for you this year says learning about generator motors as a part of investigatory study. Questions will not be asked. The board syllabus doesn't include that, but you should know that. So we will also discuss about that. Okay. So initially, when we start discussing about magnetism, so it comes, we need to think about something called magnets. Magnet. And the concept of magnet is actually dates back to BC periods. Chinese also used to have magnets. So if you know, there are stones were discovered. Those days minerals were discovered. So there was a stone they discovered and they called that stone as lodestone. Lodestone means those days army and soldiers, they used to wear what? They used to wear shoes which used to have iron below their shoe soles. So they used to come across some stones which actually used to stick to their shoes. Now, why they named it as lodestone? So one of the reason was when the small piece of stone was kept on a pivot means, like a triangle, the stone used to always point towards the north. And that north was not known in those days. Those days, north was known by pole star. Pole star, what in Hindi we call as Dhruv Tara. So it was pole star, and pole star's name is lodestar. Another name of pole star is lodestar. Since the stone points towards lodestar, they used to call it as lodestone. Lodestone is a big mutual fund company also in US. Okay, so that's called as lodestone. After that, studies, what we need to now understand is about magnets and magnetism. So when we talk about magnetism, the difference with electricity is while the concept of unipolarity exists in electricity, unipolarity means a positive charge exists in electricity, magnetism is always a dipole. Means you cannot have unipolar concept. You can't have a north pole, you can't have a south pole separately. So if you are a magnet, you will have a north pole and you will also have a south pole. Okay? Initial part of your chapter, we will discuss some very interesting facts about a magnet. So as a student of science, some things should always be there with you. If you love science, one of those things is a magnetic compass should be there with you, and some bar magnets should be with you. So let's say we have a bar magnet. Okay, let's say we have a small bar magnet like this. Okay, and if you tie this bar magnet and you suspend it, if we tie the bar magnet and we suspend the bar magnet from top. Okay, so what I'm trying to say is this is my magnet and this is right, yeah, and I suspend it from the top and it is tied with a string. So let's bring our string also. So let's say this is tied with a string out here right at the center. It's tied with a string right at the center. Okay, it's tied like this, say with a string at the center. You will find that when the magnet is allowed to freely suspend, this magnet will always align itself along the north-south direction of the earth. Okay, so we say, but there's some interesting findings out here. It points towards the north and it will point to align itself to the north-south of the earth, right? Side which is pointing towards the north of the earth will be named as the north pole. The north pole of a magnet, and this side will be known as the south pole of the magnet. Is this understood? So question comes, why is this magnet aligning itself in this way only? Means if you twist the magnet also, the magnet ultimately does what? It comes back to its original position. So what people started thinking, and the laws that came up was that if you look at the earth now, okay, let's have a look at the earth. This is my earth, all right. And what I now do is that I take up this thing, okay, and say I clone it, fine, and I make it small. This thing, if I put it here, it is actually aligning in this way towards the north and south of the earth, which makes people think, well, why is it doing in this manner? And if you twist it, it again comes back in this particular orientation. That means there is some magnetic field of the earth also, something which is there hidden in the earth, which you and me right now don't know. So whatever is hidden in the earth is basically the earth's core is also behaving like a magnet. Okay, now there will be some interesting study now. The earth's core is also behaving as a magnet. This is the core of the earth. And if you see what is the core of the earth, the core of the earth contains all molten metals, right? And they are in molten shape, so they're creating a current which actually behaves like a magnet. Brings us to one more interesting study now here. That means if I extend these lines which I had drawn earlier, right? These lines which I had drawn earlier. So this is not the North Pole that you see. So this was named as the magnetic axis of the earth, or the magnetic meridian. This is the magnetic axis of the earth. Have you understood? Now please understand, initially the bar magnet which pointed towards the north, this side was called the North Pole. That means if I look at the magnetic axis of the earth, the earth's magnetic axis should have a south pole on this side. Do you agree or not? Because north will attract the south. And this side, this is the magnetic axis. This is the north pole of the earth's magnetic axis. This is the magnetic axis, right? However, in geography, you have studied that you have what? You have the axis of the earth on which the earth is actually rotating, right? So we have an axis of the earth also. Let's say this is the axis. This is called the geographic axis of the earth. So this is my geographic meridian, or the geographic axis. And in geographic axis, this is my geographical North Pole. Do you agree or not? And this is the geographical South Pole. Don't confuse between them. And if you are interested, then this angle is around 11.5 degrees. So if you take a magnetic compass and you are, say, in the BC period, Odyssey period, and you start sailing, you actually will not go to the north. You will drift away 11.5 degrees. 11.5 degrees is a huge drift. You will actually go beyond the north. And this particular, what you call the pole star, is actually here. Pole star is here. Have you understood? This is the Earth's geographical axis, geographical north. Since a bar magnet faces this side of the bar magnet is called North Pole. But it doesn't face this, it actually faces this side. Axis of the Earth is a little bit, off from the magnetic axis, that is around 11.5 degrees. Modern day, if you take a mobile phone and you switch on your compass, modern day compasses are calibrated for this error. So if you take your mobile phone and start sailing, you will actually go here only. Have you understood? But actually, if you take a magnetic compass needle, you're not going north. And this is quite big. In the language of missiles, we call it as CEP, circular error probability. Suppose you have shot a missile from here to a target. What is the circular error of that missile? Means how far it can fall. A simple 1 or a point some minutes error can lead the missile to land at 4 kilometers apart, depending on kitna dur se aa raha hai. This is how much? 11.5 degree. This will drift you quite ahead. Is this concept understood? And the magnetic materials which are magnetic are usually will be cobalt, nickel, and iron. Only these three things will show magnetic behavior. In higher classes, you will study things like ferromagnetic, paramagnetic, diamagnetic. So at your level, you should know that this is a concept. Understood? This is the geographical part. चलो एक step और आगे चलते हैं. Can we go ahead? Okay. One step more. Now, if you have a positive charge, we always do things with a positive charge Q, then there is a region around the positive charge. How big is the region? Sir, the region actually is spreads till infinity. Question is, as more and more you are near to the region, you will actually feel the impact of the charge. 1 minute, huh, bacha? You will be feeling. Yeah, you will be actually feeling the impact. So let's say I have a region around Q. If you have a region around Q and you bring another charge in its vicinity, depending on the polarity of that charge, we generally bring a test charge. Test charge is also positive. So you'll feel a repulsive force. And if your test charge was negative, you feel an attractive force. The more nearer you are, the more will be the effect of the force, either attractive or positive. And if you take this charge at infinity, still there is some interaction which you cannot feel. Like if I am a big dada or a gunda of my area, there is some effect of me in Delhi also. Question is, you are not feeling it. Are you getting it? So this region or space, we say that there exists something called an electric field. An electric field. Nothing difficult for you to understand this concept. If you just go like this, say, let's say, instead of charge, you say that this is a celestial body. Let's say this is Earth. Then in and around Earth, every object will be attracted towards the Earth. Then in that case, what do you call it? Gravitational field. Yes or no? So when you launch a satellite has to escape the gravitational field, otherwise it will come back. So in and around a charge, we have electric field. So in and around a magnet, we will have the magnetic field. Okay. So in and around the magnet, what we have is known as a magnetic field. Magnetic field. And this magnetic field is also a vector quantity denoted by B. Like electric field is denoted by E, magnetic field is denoted by B. Ye zarurat padega in grade 12. Right? And it's a vector quantity. That's why this is mentioned. It's a vector quantity. And the SI unit of this magnetic field is Tesla, denoted by T. Okay? This, yeah, Tesla. Clear? Right. So let's take, now for us, we now will do what? Just like in ray optics, you saw some ray diagrams. Those ray diagrams are imaginary geometry that you do in order to support your ray diagrams. Otherwise, there is no ray which is coming out and going through the focus, but everything happens according to it. For that, here also we will develop a concept, and the concept is called magnetic field lines. Magnetic field lines are actually imaginary lines, okay? These are imaginary lines. Imaginary lines, or you can, they are also like a curves, imaginary curves, and they have all been designed to study magnetic field around a magnet or magnetic field. Now, how does that help me? Like ray optics, all the rays were designed to study the image formation. To understand magnetic field, we will design a concept called magnetic field lines. Is this understood? So the magnetic field lines are, now there are some assumptions with which we study with the magnetic field lines. For that, we will initially take a bar magnet, right? And this bar magnet will have a north pole on one side and will have a south pole on one side. अच्छा, another question will be, sir, इसको मैंने बीच में तोड़ दिया तो you will get a north pole there and a south. So automatically it will align itself. Okay. Now magnet, now there is, now this is, there's a magnet, there is a Dadagiri zone around it, which is known as the magnetic field lines. So there are some properties which you should know as a grade 10 student, and this is asked. I will write the properties, but first I will draw those so that it becomes easy for you to understand. Magnetic field lines are lines or curves which are designed imaginary. First of all, the word is imaginary. They are actually plotted to understand the magnetic field or the behavior of the magnetic field in and around a magnet. Such lines originate from the North Pole and terminate into the South Pole outside a particular bar magnet. How does this line come? Now this is important. How does this line come? What is a magnetic field line? This is the path traced by a hypothetical, means kalpanik, hypothetical solo North Pole if allowed to move freely around the magnet or magnetic field. Understand this. Sir, you just said that magnetic poles cannot be independent. I know that. That's why I'm saying hypothetical. Suppose you would have separated one North Pole. Suppose. Then how the North Pole will go, and you bring the North Pole here, he will say, hey, so he straight away moves out from here, and the South Pole tells him, acha, acha, and he goes to the South Pole. So the magnetic field line is the path traced by a individual, hypothetical, solo North Pole if it was allowed to roam freely in and around the magnet or a magnetic field. Children, why I'm writing magnet and magnetic field? Later you will study a current can also create a magnetic field. It's not that you have to always bring a nickel, cobalt or some item. Earth also has a magnetic field. So how do we do this? In order to do this, we take the help of a device. I mean, you can do this at your home also if you want, okay? All you need is a small magnetic compass. You take a magnetic compass, and this magnetic compass will have what? It will have an arrow which will be directing towards the North Pole always, right? This particular compass, now see, this particular compass is then taken and it will be placed exactly here. This is in fact an experiment in grade 12 where you are supposed to plot the magnetic field line. So you will take the compass and you will take it out here. You will first see that the compass will be first pointing in this direction. The compass will be pointing in this direction, like this. So as a practical student of physics who is doing practical, he will put one dot here and one dot here. Have you understood? One dot here, one dot here. The next job that you will do is that you will now put the compass in such a manner. Let's say this is my compass, and 1 minute. My next job would be that I would take my compass. The next job will be you take your compass, and wherever you got that arrow's point, right? You had got it here. Means you had got it here. You now put your compass on your next orientation right out here, and you will see that your compass has now deflected in this manner. In this manner. Did you get it? So you put your next dot out here, and now you have understood. If you put your compass here, slowly the needle will rotate. So actually how the North Pole is moving. So what are magnetic field lines? A magnetic field line is the path that is traced by an individual North Pole, hypothetical, if allowed to move freely around a magnet. Right? They are imaginary, but they have been plotted for us to understand the magnetic behavior. Magnetic field lines originate from North Pole and terminate at South Pole. So let's add some more magnetic field lines and make it interesting. So they will originate from the North Pole and terminate at the South Pole. By the way, you should add the word in the exterior of the magnet. However, inside the magnet, they will always move from South Pole to North Pole. Inside. ये सब लिखते जाओ, हाँ. Inside the magnet, they will always move from south pole to north pole, and the magnetic field inside a magnet is always uniform. This is uniform, means whatever is the strength here is the same strength. That's what we are talking inside the magnet. Inside the magnetic field, strength of the magnetic field B is constant. That means it is uniform. So what all did you write as properties? Number one, imaginary. पैदा कैसे हुआ? By a north pole. Originate from north pole, terminate at south pole. Next point is inside the magnet, they will always move from south to north, right? And the magnetic field lines will be parallel to each other, which depicts that the magnetic field inside a bar magnet is always constant and uniform. Why do I say it's a vector quantity? If I say constant, means only the magnitude is same. When I say uniform, the magnitude is same, the direction is also same. Clear? Have you understood? Okay, now what I'm doing, I'm tracing one more magnetic field line like this. Oh, I'm tracing one more magnetic field line, and say this magnetic field line is this. I'm tracing one more magnetic field line, and just like this. The next point, no two magnetic field lines cross each other. No two magnetic field lines cross each other. Have you written? What is this point number? What in your book? Fourth. So my mistake, you need to write a 3.5 point also before fourth. You just write no two magnetic field lines cross each other. Okay? But before that, I missed out something. Let's say what we missed out. Understand? Suppose I take a small point P out here. This is a point P, and you ask me, what is the direction of the magnetic field at the point P? You are asking me what? What is the direction of the magnetic field? यहाँ पे तो field का एक direction होगा ना? Where is the direction? So the direction is actually given by, the direction will be given by a tangent that I'll be drawing at P. Tangent, you know, line that joins the, let's say, it will be given by a tangent drawn at P. Now, which side should the arrow be? Look, which side is the arrow of the curve in this side? So the arrow goes in this side. So our 3.5 point, which I missed out, would be the direction of magnetic field at a point is given by the tangent drawn to the magnetic field line or the magnetic field curve at that point, with the arrow pointing in the direction of the magnetic field line. चीज को समझिए और अपने words में लिखिए. There is no need that you have to tail my words. The magnet. See what did we understand here? Magnetic field at any point is given direction. Direction of magnetic field at any point is given by a tangent drawn at that point with the direction towards, or the direction in line with the direction of the curve at that point. So if the curve is going this side, then the direction would be in this side. Similarly, just for your what you call clarity, suppose I want to find out there's a point P dash. There's a point P dash, and I want to find out what is the magnetic field at P dash. I will draw a tangent here. Arrow is this side. So this is the magnetic field at this point, right? So it was imaginary, designed to understand the magnetic field around a magnet. Then path is traced by a horizontal north pole, not horizontal, hypothetical north pole if allowed to move freely around the magnet. These lines originate from the north pole and will always terminate at the south pole. Inside a magnet, magnetic field lines are uniform, magnetic field lines are parallel, which shows that the magnetic field is constant and uniform in terms of both magnitude and direction. The direction at a particular point is given by the tangent drawn at that point, with the arrow inclined with the direction of the magnetic field line at that particular point. Itna ho gaya? Now, point number 4, which we had written, no two field lines can cross each other. Now let's understand that. No two field lines can cross each other. Let's say I have a field line. Let's say I have a field line which is line 1 and I have a field line which is line 2, and they are crossing over at a particular point which is say Q. Okay? Method of contradiction. They are crossing over at Q. Right? They're crossing over at Q. Now, if they cross over at Q, my question would be, what is the direction at Q? Right? What is the direction at Q? And let's say the magnetic field lines are pointing in this direction. My question is, what is the magnetic field line? What is the direction of the magnetic field at Q? So one way would be that I draw a tangent to this L2 line. Do you agree? Then this is the direction. Then you can counter me and say, sir, why are you so stepmotherly towards L1? You could have drawn tangent to L1 also. I said, yes, that is also correct. So for a particular point Q, I am getting two different directions, which is not possible. Understood? Therefore, two magnetic field lines never cross each other. फिर से एक बात समझते हैं. The statement we are making is magnetic field lines do not cross each other. Okay, Shreya, your camera has gone more on the ceiling. Do not cross each other. So why do you have to? You pay attention here, na? So the magnetic field lines do not cross each other. If they cross each other, let us suppose, then we have a point of crossing which is Q. Then the direction at Q can be drawn by honoring the previous statement, either for L1 and or for L2, which will result in two directions for the same point. How can one point have two different directions? Not possible. So we write, no two magnetic field lines can cross each other, because if they do so, now I want you to draft your answer. आप लिखो. आप समझे हो ना? Why two magnetic field lines cannot cross each other? Have you understood the concept or not? Now it's all about English. Let me see how you draft it. ये हो गया चैप्टर स्कूल में? कैसा तो कुछ बताया नहीं होगा? Yes, sir.
Then just because a compass needle cannot point at 2 points at once, right?
There's nothing about a why are we bringing a compass needle? Then you're making yourself, handicapped with a compass needle. I would say I cannot have two tangents. A single point cannot have two different directions for the same magnetic field. Ask yourself, Anurag, this magnetic field is created by this bar magnet, right? So every point has to have a unique direction. But if your assumption was correct, then this is a point which is not having unique directions. It is pointing somewhere here, pointing somewhere there, which is against that particular concept. So I would have written, no two magnetic field lines can cross each other, because had they crossed, we would have two directions for a same point, for the point of crossover, which is not possible. Otherwise, we would have had two different directions for the point of crossover. Likhna, khud likhna, beta, this you have to learn to draft your answers. We are just talking about something in English. You may write 2 words more than him, or you may write 3 words less than him. As long as your point is mentioned, point is very simple, that if you cross, then at the point of crossover, there will be two different directions. Yeah. And if you are not able to draft, what is your weak, where you are lying weak? You are lying weak in your reading and listening skills of English as a language. I have said this to grade 8 the other day. Please watch content. Content means nice documentaries, TED Talks, where people talk. You are now a grade 10 student. What 10? You will be grade 11. At this age, you should learn the art of conversation. Your conversation should be grammatically, vocabulary, punctuation-wise correct, and should also have snippets of humor, so that the other person enjoys talking with you. If you feel that what is happening in your case is that you are having conversational English which is not correct. You re, yo bro. And when it comes to academic English, it needs more precision. If you go by our days, I have never spoken to any of my friends in English. I studied in convent, but after that I studied in KV. So Hindi was our language, whether it is slang, Because we can never say, I will slap and take all your teeth out. We will always say, "Eh, thappad maar ke muh tod dunga." Feel is far better. But how did we learn English? I passed my grade 10th in 1993. March was my exam. Up till 1991 was Gulf War, when Iraq was invaded by US. Those days, cable TV came to our house. I could not follow anything what they used to say on BBC. I have no shame in telling you. I never used to watch any English movie, and whatever Spider-Man used to come up, that was English without subtitles. So we only thought that we should just watch the graphics. If someone is there who has helped me to understand the follow dialect is the 1992 series of Indian cricket team. They went to Australia for a series and stayed there till the World Cup for almost a 4 month stay. And those 4 months, I used to be glued to the TV. And by that time, it picked up. Not that I could not speak English, but I could not pick up the foreign accent. हमारे जमाने में इतना कौन सा इंग्लिश मूवी आता था? आपके तो कितने अच्छे से एडवांटेजेस है. There's a lovely documentary channel called I Learned Science. A girl narrates stories of sinking of ships and all. The way she speaks, she takes you to April 12, 14, 1912 when you are also on Titanic. And with graphics and all. तो ये जो आप लिख नहीं पा रहे हो ना, you know the story, but you're falling short of articulation. चलो, anyways, हो गया? Node field lines. So these are very common question. Define magnetic field lines or magnetic lines of force and state their properties. Another question that I can get is, why do two magnetic field lines not cross each other? Understood? That's all about the initial part of magnets. Let us now get inside the chapter. And then you can also understand, is there a magnetic field in the human body? Yes. There are current. Wherever there's a current, there will be a magnetic field. That's why you do MRI. Right? If you go for an MRI, you know, where the body is put inside that tunnel. And there will be no one in that room. Dreadful experience, huh? Twice I have done. And they will give you one switch in your hand. If you feel claustrophobic, you're just supposed to press that switch. And the body goes by the head inside. And you should not have any metallic thing in your body. And then the magnetron will rotate and make huge noise. Oh, that is in your body, there should not be anything. And the machine comes from good companies like all these Siemens and all, but they will actually codify the word they'll say, Hyderabad is very good. You go to the good hospitals, andar jaake bolna, stop bolna. And they're saying Telugu and something. Half the thing you will not listen. And you have to close your breath. And it takes you inside a tunnel. Almost till you have to hold your breath until your ankles, it will go inside. सांस नहीं छोड़ना, गया फिर. Again, they will do another 7,000 rupees.
That's the whole scan.
A whole scan. The body will go, then the magnetron will rotate. Sound will take around 30 seconds. Tora 30. Abhi saans band kijiye. He will say, and then it will make a noise. You just feel that jaldi nikalo. See, when my kidney stone happened, the MRI will spot anything on your body. Anything. And if your body cannot spot, then they do a high contrast MRI. That is, in your legs, they will give one injection. Dyes will be inserted. Yeah, hello. God forbid those happens. So we now come to the famous thing, which is known as Oersted experiment. Oersted's experiment. Oersted's experiment is also serendipity. Do you know what is serendipity? When you actually look for something different and you get something different, and that something different becomes more important. Alexander Fleming's discovery of penicillin is also serendipity. So his name was, Danish guy, his name was Hans Christian Oersted. And the Christian is written in K. Hans Christian Oersted. O-E-R-S. So what was Hans Christian Oersted doing? He was actually trying to study heating effect of current. Means when you pass current through a wire, the wire should get heated. So our friend Hans Christian Oersted must have done some setup which was something like this. He must have had a wire like this, right? And then, so this wire, he must have connected an electric circuit. Let's say he had connected a electric circuit like this. He had connected an electric circuit like this, and his circuit comprised of a wire. Obviously, this is his key, and this is his battery or cell, whatever you say, plus minus. And if the key is turned on, then the current in the circuit would be actually moving in this direction. Don't you think so? In this direction. And later, to make it more easy, obviously the study was done like this, and then to make it more easy, say the geometry was made in such a way that the wire was made straight also. Now let's understand. So what he did, he also had in the vicinity he also had a magnetic compass, and this magnetic compass, when nothing, he has not turned on his, sorry here children, he had a magnetic compass, say like this, and when the magnetic compass was not, the circuit was not turned on, obviously my magnetic compass must be facing in the usual north-south direction. Now the interesting thing happens. As soon as Hans Christian Ørsted turns on what you call this circuit, he turns on this circuit, he observes that there is a deflection in this particular magnetic compass. There's a deflection. First, try to understand the story. There's a deflection. As of now, we are not going by which side it is deflecting. There's a deflection, and when he again opens the circuit, means turns it off, he finds that the needle is restored back. Okay, so let's see what is his first finding. His first finding was, let's see his findings. Okay, his finding was that the needle deflects as the circuit is turned on. And see how you study physics. Circuit is turned on, it means as I flows through the wire, it deflects as soon as the circuit is turned on and gets restored to its initial position in higher grade engineering and science. We write position as px. Sikho thoda sa. Initial position as the circuit as I is turned off. Okay, so what, in short language, what will I say? As soon as the I flows into this wire, the magnetic compass shows a deflection, and as soon as the circuit is turned off, the magnetic compass is just, the needle restores back to its original position. So we should start thinking, was there a magnetic field before it was turned on? Yes, the Earth's magnetic field you cannot rule out. The Earth's magnetic field is there, that's why it is pointing towards the north. But after I switched on, some additional deflection was seen. That means one new dada must have got created, whose additional dadagiri is also coming up. And now this needle is behaving as the vector sum of Earth's magnetic field and the magnetic field created by this wire. It must, like I was earlier being pulled by this side, as soon as the circuit is turned on, I'm pulled this side also. So where will I go? The vector addition of both these, right? So it must have deflected. And his very fact that as you switch it off, okay, this is a current carrying wire, it will also develop heat. He was studying that. As soon as you switch it off, it restores back. That means whenever current flows through a wire, a magnetic field is created around it, and the magnetic field disappears as soon as the current stops. One of the greatest finding about this is, if you had had a bar magnet out here, just remember, if you would have had a bar magnet, could you actually abolish the magnetic field? No. You actually created a slave. जिन पैदा कर दिया है आपने, who at your choice comes on and at your choice goes away. Yes or no? But he is a human being. Whenever we create something like that, we then see, can he do everything that I want? So he did another thing. He changed the I polarity, the current's polarity. Means what he did, he swapped this battery terminals. Now he finds that the deflection is equal to previous but opposite. Wow. But opposite in direction means my slave is now actually my slave. That means the polarity of the magnetic field depends upon the orientation of the electric field. If the polarity of the current is reversed, the magnetic field's polarity also gets reversed. However, for the same magnitude of current, the deflection remains constant. For the same current, the deflection remains constant, but the deflection happens in the opposite direction. So first thing, what did we see? Magnetic field exists as long as current flows. Disappears when you switch off the current. Second, what did we see? If the same strength of the current is reversed in its polarity, magnetic field is again created, but now in the opposite direction with the same strength, because the deflection is similar, but opposite in polarity, and again the same thing, that it disappears when you switch it off. Now the third thing came up. मेरे लिए और सोना लाओ. He increased the current. Then he found that the deflection is proportional to the current. If the current increases, the magnetic deflection also increases, which shows that if you increase the current, you are basically increasing the magnetic field. So my third thing, on increasing the current, the deflection was found to be more than the previous occasion, which infers that the strength of the magnetic field depends upon the current, which is a direct relationship. More the current, more the magnetic field. So now he is my real gulam. I can bring him when I want. I can turn him to my way, and I can also increase his intensity to my choice. That means if I reduce the current, the magnetic field also reduces. Do you agree or not? Very good. This was Hans Christian Oester's experiment. Something more we will learn, but I just take you now to a real life scenario. Let's go for a real life scenario and see. All this we have learned, but what is the use of this learning? This is what I feel schools don't tell you. What is the use of this learning? Now this is, say, our great friend Anurag's living room wall. This is the wall of his living room, and he has purchased one excellent 75-inch OLED television, and he now wants to install it on his wall. And I am his electrician or the installation guy who will come. He has booked our friend Anurag is, what happened, darling? I am giving you an example and you are vanishing from the screen. Okay. So this is Ali's screen. Gone. And Ali has bought one 75-inch TV and he wants to install it. So he has booked a call with Amazon installation guy. And I have come, Srinu electrician with chappal cladded. And first I tell him, sir, ekra install chesi sir. मेरे को तेलुगु नहीं आता है. I speak it. Okay, sir. Where fit, sir? Oh, just behind the, what do you call, sofa. Okay, sir. Hey, Babu, drill machine ready, Jesse. You'll immediately start your drill machine because we have to put bolts in it. And immediately I start drilling out here. Have I ever come to Ali's home before? No. But Ali's house is a fantastic house which was designed by some interior decorator in a very fantastic manner. And that interior decorator gave a nice feel, एकदम lights controlled, ये नील के घर जैसा. तो अंदर में क्या क्या electrical contractor, that contractor must have done a lot of concealed wires are there. Now wires are going through the wall. हो ही सकता है ना? These are some wires going through the wall. This is inside, huh? And I am Srinu electrician. And I'm actually without, and when we enter somebody's house, we'll be opening our sandals. Look like idiots, like Indians, we are idiots when we walk. So with barefoot, I have come and now I'm drilling his wall, and I've punctured one wire. And then what is happening? Shock laga, 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 and I am also vibrating along with it. Have you understood? And then job done. After that, somehow my life was saved. I will go back and I will narrate this. Oh, दूसरा week में ना वो एक घर को गया शेखपेट में, अब्बा बाबा बा जैसा ड्रिलिंग मारा पूरा शाक लग गया जी मेरे को. मैं खोला किधर से, वायर जा रहा था जी अंदर से. This is how idiots work. But if this job would have been done in US, there the installation cost is very high. The guy would have come and said, so sir, where would you like to fix your television? He says, out there. I like to sit on my recliner and watch Odyssey from here. Good. So he'll immediately say, Paul, got the gauge with you? He'll first take out a gauge and he will move it on the wall. Small gauge. And then he says, tick, 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 it makes a noise. No, sir, we can't do it there. You got wires running behind it. That guy is just using Hans Christian Oster's experiment. Current carrying wire behaves like a magnet. Because I don't stay in your house. How do I know what is there inside? He will never drill. He will never drill. In fact, it happened with me once. I say so many things. I have also done some idiotism. Different. My mom, she can't walk that nicely. So for her, I had to fix one hand shower. You know the hand shower? So for that hand shower, I need to, everything is done. Now the shower hooks have to be fitted where the shower will be kept. So I said, this place is fine? I asked my mother. She said, yahan theek hai, I can take it out. So as soon as I ruptured it, just like the last scene of Mahabharata, Bhishma Pitama wants water, na? Arjun shoots an arrow. Immediately from the wall, patch, water comes from my face. What did I do? I punctured the pipe inside the wall. How do I know how the pipe is running? So what is the story? Get a PNID, piping and instrumentation diagram, before you do that drilling. That small drill. Now water is coming out at full space. The first thing, we close water. Now see next day how much job goes. All tiles had to be removed. That inside pipe had to be cut. Another additional pipe had to be put. Again, the house is now 12 years old. Where do you get a matching tile? Nearest matching tile from some end tower had to be procured. That small idiot step of mine making the job go so big. The same thing you can have done here also. So you're using Hans Christian Oster's example. Current carrying wire behaves as a magnet. And in every house we have got false ceiling. So many wires are running. तुम्हें कैसे पता है inside wire गया? Otherwise you would have drilled. And he will say, "Abba, ऐसा क्या? मैं कैसा करके बच गया जी?" Then also he doesn't understand that he created a fool of himself. Welcome to India. That's how we work. Have you understood? Fine. So is this understood? So this is actually the takeaway of what happens in the experiment of Hans Christian Oster. So what all did we find out? Our 4 findings are the current carrying. From there, we said that a current carrying wire behaves as a magnet. As a magnet. And when a current carrying wire behaves as a magnet, there are some properties associated with it. That the magnetic field comes into existence when the current flows through the wire, disappears when there is no current, changes its polarity with the change in polarity of the current. The strength varies directly along with the current strength. More is the current strength, more is this, right? And then what we need to now know is that what is the direction of this magnetic field. So magnetism is known as हाथों का खेल. The entire chapter, will study only one law. There are many laws, okay? Direction of this magnetic field. So magnetic field. So this magnetic field's direction is, there are 2 rules we can say. One we say is the right hand thumb rule. The right hand thumb rule. Okay, or you can also say, have you seen a champagne bottle or a bottle opener? You have a cork on that. So it's called the corkscrew rule also. Either ways you can say. This is more preferred, but anyways, in vector diagram, we use this also. So how did you do it? You will take your right hand and your thumb should actually follow the current's direction. And then what you will do, you will curl your fingers. We'll see that. Curl your fingers, and that will actually tell you the direction of the magnetic field. So if I put, now look at this current, the current is going on top, right? The current is going on top. So your thumb will be something like this and your fingers will be like this. So you will curl your finger, which tells that the magnetic field lines are actually circular loops whose orientation will be in this direction. Just see. Got it? And if we reverse the polarity, current comes down and then the rotation just changes. You can do it. Majo ayo? Understood? It will be in this direction as long as it is in rotation, and if you come in this direction, it rotates in the opposite direction. Okay? So Oster's experiment is very important, and when we study grade 12, if you just go through grade 12 video of moving charges and magnetism, go to lesson 1, the first thing taught is this thing again. Whatever you have learned here is the same thing taught in grade 12. If you have interest, you can go to that video also and see moving charges and magnetism, the first chapter, first lesson. Is this much fine? Okay, how much time do we have? Okay, we can do something more also. So after this, we come into straight wire. From straight wire, we get into a loop, just a little bit. We get into a loop. So a loop will be something which is circular. Something which is circular. And this loop is actually connected to. So if you see your current is flowing in this direction, then current is going in this direction, coming back in this direction, this direction, this direction, this direction, this direction, I. Okay. Now, if you see a small section of your loop, let's say we see this much section of the loop, and the loop is pretty much long, of high radius. This section, that is the section XY, can be considered as a straight line. Any section of a loop can be a straight line. Take your cycle and between two spokes, you just cut off the rim. It will come as like a straight line almost. So I'm just removing my XY position. Aha. So let's say this much position is the XY. How is the current better? The current is going upwards direction. Upward direction, right? So imagine yourself that you have actually put a cardboard through which this item is coming out. Means I will actually abolish this much part. Do you now get it? Imagine that it is coming out of cardboard and that much portion is XY. Put your right hand thumb rule. So you again get concentric circles. Concentric circles which will be moving in this direction. Right? Moving in this direction. So here I will be getting concentric circles. So 1, 2, 3, and all direction will be And if you see on this side, how will you see them? Just the opposite way. Because here, now this is coming down. So everything will be in this direction. That's all for today. The magnetic field lines the magnetic field lines for a loop and for a straight current carrying wire. The rule that we apply is right hand thumb rule. In a loop, we take a portion of a loop which also resembles like a straight line. And in that straight line, the same concept is applied. Okay? Then we will see polarity in our next class. Okay? Hello.